So this is our first question from the topic. The second set of topic in work energy power, which deals with law of conservation of energy and momentum. So the question says two bodies are having kinetic energies in the ratio 16:9 if they have the same linear momentum. The ratio of their masses is. So let us consider this question by detailing the given parameters of the two bodies, body 1 and body 2, as m1, v1, p1 and k1, linear momentum and kinetic energy, and m2, v2, p2 and k2. It is given that the linear momentum is same, therefore we have p1 is equal to p2, which otherwise gives us m1 v1 is equal to m2 v2. Also, k1 is half. Okay, let's try now. So k1 is half mv1 square, or in other words it can be written as p square by 2m, right? Because kinetic energy is p square by 2m and kinetic energy 1 is p1 square by 2m1. Similarly, k2 would be p2 square by 2m2. Now okay, now it is given that these two bodies have the kinetic energy in the ratio 16:9, which means k1 by k2, right? K1 by k2 is actually equal to 16:9, which is p1 square by 2m1 by p2 square by 2m2. So I can write p1 square by 2m1 into reciprocal of this, which is 2m2 by p2 square. Now it is also given to us that they have the same linear momentum. What does it mean? P1 is equal to P2, which means P1 square should be equal to P2 square, and therefore P1 square by P2 square can be written as, or P1 square can be written as P2 square, right? And therefore P2 square by P2 square would be equal to 1, right? So P2 square by P2 square will be equal to 1, and therefore we get as 2 by 2 is 1, so we get 16 by 9 is equal to m2 by m1, and therefore m1 by m2 will be equal to 9 by 16, which gives us the correct answer as option D, 9 is to 16. Okay, so that was question number 1 in this topic, law of conservation of energy and momentum. Okay, so next question is the second one, which is based on law of conservation of energy and momentum. So see, what we'll do is we'll try to solve this question in two ways. One, we'll try to do is using the concepts that we learned in laws of motion. Two, we'll try to do it using work energy theorem. Okay. So in this question, let's try to first solve this question using laws of motion. Okay. So what is statement 1? A truck and a car moving with same kinetic energy. So we have a truck and a car, same kinetic energy. So KE1 and KE2 are the two kinetic energy, and we can say that this is equal to KE1. Are brought to rest by applying brakes which provide equal retarding forces. So we have braking force 1 and braking force 2. Okay. Both come to rest in equal distance is the claim. So we go for the hypothesis that S1 is equal to S2. All right, let's see how and let's see why. Oh, if at all they are. So if I were to go with the free body diagram of the car, right? Because free body diagram of the car, I can say that the only force acting here is the braking force, and the net direction of motion is towards the right, right? Okay. Now, if we combine the free body diagram and apply second law of motion, we know that since this car is moving only in the horizontal direction, there is no motion in the vertical direction. Therefore, sigma Fy will be equal to 0. And sigma Fx will be equal to m into Ax. Now, what is sigma Fx? Sigma Fx implies sum of all the forces acting in the x direction. Now, this is the initial condition of the car. This is the final condition. Since it is coming to rest in equal distance, we can say that the final velocity is equal to 0 and initial velocity is equal to u. Now, since the braking force is applied, we can say that sigma fx is equal to bf. But what we need to understand is the net direction of motion is towards the right and braking force is applied towards the left. Therefore, while considering sigma fx, we need to consider the direction which is minus bf. So we have minus bf is equal to m1 a1. Why? Mass of the car we have taken it to be as m1, ax is a1 for the car. Okay. So what is a1 from here? A1 here is, my bad, it's minus bf by m1. Okay. So I'm not including any concepts from work energy power. All what we learned is, or all we have applied is the concept that we learned in, the concepts that we have learned in laws of motion. Now let's see the same case with truck. As we have it in car, for the truck, the only force acting in the x direction is the braking force, and net direction of motion is also towards the right. Initial condition, final condition, truck comes to rest. There is no motion in the y direction. The motion is restricted along the x direction. Therefore, sigma fy is equal to 0, and we have sigma fx is equal to m into ax. This time it would be m2 a2, and sigma fx, sum of all the forces acting in the x direction. There is only one force which is acting in the x direction, and since the net direction of motion is towards the right, we'll take all the forces acting towards the right as positive, and we'll take all the forces acting towards the left as negative, and therefore we have bf is negative, and therefore pf would be equal to minus bf would be equal to m2 a2, and a2 is therefore minus bf by m2, right? Now what we'll do is we'll bring these two concepts together, and what do we get by that? So from the car, we found out that a1 is equal to minus bf by m1, and what is a2 is equal to? A2 is equal to minus bf by m2, right? Now we'll apply Newton's equations of motion. V square minus u square is equal to 2as in both the cases. Okay, so in the first case we have Vc, which is velocity of car, Vc minus Uc, final velocity of car minus initial velocity of car, and similarly final velocity of truck minus initial velocity of truck. In both cases, Vc and Vt, what are they equal to? They're equal to 0. So final velocity is equal to 0. Why? Because they are coming to rest. Therefore, what we get is Uc square is equal minus Uc square is equal to 2 into a1 into s, minus Ut square is equal to 2 into a2 into s2. What have we derived from now? We have derived that a1, right? We have derived that a1 is equal to minus b1 by m1, minus bf by m1. So we have a1 is equal to minus bf by m1. And what is a2? A2 is minus bf by m2. Now I'll do a slight rearrangement here. I'll take this 2 to the LHS. I'll take this 2 to the LHS. So what we have is minus uc square by 2 is equal to minus bf by m1 into s1, and minus ut square by 2 is equal to minus bf by m2 into s2. See, now those who are figuring out, just trying to figure out the relationship between work energy theorem and this question, you have the answer right away. Well, I'm not going to solve it in that way because just for you to think. So pause the video here. Try to think how could you derive with the same equation using work energy and power. I repeat, the answer lies here. Okay, all right. Now we'll continue here. So we have minus uc square by 2, right? And minus bf by m1. See, what I'll do is I'll take this m1 to the LHS. So we have m1 into uc square by 2. I'll cancel off these two negatives. So this negative by negative becomes positive, negative becomes positive, right? Similarly, if I transpose m2 to the LHS, m2 into ut or u2 square by 2 is equal to minus bf. Okay, cancel off this minus here. S2, right? Now, what is m1 un square by 2? Half m1 un square is exactly half m1 un square is kinetic energy of car. Initial kinetic energy. What is m2 u2 square? It is initial kinetic energy of truck. Now, if you divide these two, what you get is kinetic energy 1, right? I'll just go a bit more further. Yeah. So what you get is kinetic energy 1, m1 u1 square by 2, kinetic energy 1, by m2 u2 square by kinetic energy 2 is equal to bf by bf is 1. Of course, I forgot to cancel out this. That becomes 1. And all we get is s1 by s2, right? By s1 by s2. And what does this imply? This implies that BF by BF will now become 1. So it is given, we could derive that KE1 by KE2 is equal to S1 by S2. But what is given in the question? It is given in the question that the cars have the same kinetic energy, and if cars have the same kinetic energy, then KE1 by KE2 should be equal to 1, and therefore S1 by S2 should be equal to 1, which implies S2 should be equal to S1, and therefore both of them will come to rest in the same equal distance. Okay. Okay, so that's statement number 1. Now let's see what happens in statement number 2. A kind of tricky statement, I would say. Statement 2, a car moving towards the east makes, so let us try to visualize this. So a car is moving towards the east and it takes a turn and move towards the north, right? See, you can visualize this in two ways, and based on which the of course the explanation would vary. So if I have to draw it like this is how it will go, right? Come to a rest, or maybe turn very slowly and then go like this at 90 degree. Okay, or what it can do is it can turn like this, right? Induce a circular motion there. Why is the word circular motion important? We'll come to it in a while. So a car moving towards east takes a move towards the north. The speed remains unchanged. The acceleration of the car is 0, is the statement. Let's see. When an object changes the direction while maintaining the same speed, it undergoes a change in the velocity. Why? Because velocity is a vector, right? Velocity is a vector. It will have both magnitude as well as direction. Due to the change in direction, since acceleration is the rate of change of velocity, the car experiences what? Don't go any further. The car experiences what? The car will definitely experience a what kind of force? It will experience a force that will act towards the center. Yes, what kind of force? Exactly, what we call as the centripetal force, and therefore it will attain a directional acceleration even though the speed remains constant, right? Which means the body would try to produce a motion which would tend like this, right? It will try to induce a what kind of force? It will try to induce a centripetal force here. Okay. Therefore, it can be concluded that the statement is incorrect. Why? Because the acceleration of the car is not 0. It has a centripetal acceleration due to the change in direction. So statement 2 is false, while statement 1 was correct. Okay. All right. So that's it. So let's now move on to the next question. A body of mass 5 kg is moving with a momentum of 10 kg meter per second. Force of 2 Newton acts on the body in the direction of its motion for 5 seconds. The increase in the kinetic energy of the body is. So we have two conditions, initial and final. V1 representing the velocity vector and therefore the direction of motion. And there is another force acting on it, right? So as we know, if a body moving with some velocity vector v1 is acted on a force, the velocity would experience a change and v1 vector would become v2 vector. Now, mass is given to be 5 kg, P1 is given to be 10 kg meter per second. What is P1? Is the linear momentum, which is m1 into v1. In this case, there's only one body, so we'll take m into v1. And therefore, what is v1? Will be 10 by m. Mass is given to be 5 kg, so v1 is 2 meter per second. Now see, since this F is equal to 2 Newton is a constant force and not a variable force, right? Constant force, we can say that F is equal to ma, and therefore what is A is equal to? A therefore would be equal to F by m, right? So from this equation we have A is equal to F by m. Now we can also say that by equations of motion, V is equal to U plus AT. What is V? as we have from the diagram here, is the final velocity vector v2. The magnitude is v2. Initial velocity is u, which is v1. So we have v2 is equal to v1 plus at. And what is a? A from this equation is f by m. So what is initial velocity? Given to us as 2 meter per second. Force is given to us as, okay, let me just confirm it. Yeah, so force is given to us as 2 Newton, mass is 5 kilogram, and the time is for 5 seconds. So this is into 5. Therefore, what we get is V2 is equal to 2 plus 2 by 5 by 5 is 1. So 2 plus 2 is 4. Therefore, V2 is equal to 4 meter per second. And if V2 is equal to 4 meter per second, what have been asked to find out? We've been asked to find out the increase in kinetic energy, which is change in kinetic energy, which is equal to half into m into V2 square minus V1 square. V2 square is 4 square minus 2 square, which is 4 plus 2, 6 into 4 minus 2, which is 2. So 2 by 2 is 1, and therefore 6 into 5 is, so change in kinetic energy is 30. Okay, so now we have a very good question from this topic here. Now, most of you would be wondering that I've put this question along the topic of work energy power, and I'm not doing it using any of the concepts in work energy power. Instead, I'm doing it only in Newton's laws of motion. So the question is, why am I choosing Newton's laws of motion? Because it's not that I want you to focus only on one topic. No, my intention is to make sure that you get to discover both aspects of doing one question in multiple ways. That is using laws of motion and work energy power. Okay, so I'll explain you the concepts in laws of motion, but in two different frames. One would be the inertial frame, and the other would be the non-inertial frame. Okay, and after going through both of these solutions, what I wanted to do is I wanted to solve this question using conservation of energy, or maybe okay, momentum is not possible here. Let's go for conservation of energy. Okay, and once you do that, you will come to a conclusion. Could that be possible to get the right, get the same answer using both the methods? Okay, so I want you to do that, and if you are getting the answer, do get back to me. Okay. Now, to make sure that the answer is correct, I'm doing the same question using both inertial and non-inertial frame. And what will you do? You will verify that with your answer that you have got through work energy. Yeah. Okay. Having said that, let us now move on to the question here. So we have a small block of mass 100 grams. So we have a small block of mass 100 gram is tied to a spring constant 7.9. So the spring constant is 7.9. The other end is fixed at a particular point A, which means it is this point the question is trying to mention, which is the point A. Okay. If the block moves in a circular path on a smooth horizontal surface, which means this surface, I'll just consider this to be a table. Okay, which is the horizontal, the top of the table is the horizontal surface here, which is smooth. Okay, therefore friction is equal to 0 exactly, and that is where the concept of work energy theorem kicks in. With a constant angular velocity of 5 rads per second. So this circular motion is taking is 5 rad per second. Okay. The tension in the spring is, see, now don't be worried that you've been asked about tension in the spring and it is given that tension usually what we see is in string. No. What does it basically mean? Tension in the spring basically means nothing but the force of spring or the spring force, which is equal to kx. Okay, right. Now what is this man doing here? The man is relevant here. Why? Because we are doing this question in the inertial frame. Therefore the observer is not within this moving body. The observer is in a stationary frame, right? So or a non-accelerating frame or an inertial frame. Okay, so maybe I can write down here inertial frame, this person, or a non-accelerating frame. Okay, Right. Now, what I'll do is I'll just try to make sure that you get this concept really clear. I'm gonna go in detail. Okay. I'll try to put maximum emphasis in delivering the concept. So, what you need to understand to get this concept, to get this question correct, is the difference between the length of the spring. Is the difference between length? Okay, let me just write it down. Maybe it would help you understand further. The length of the spring without rotation and with rotation. What do I mean? What I mean is when you have a spring attached to a mass, when it is not rotating, it will be at the natural length, right? But what happens is when you rotate it, right? When you rotate it, this mass will tend to pull this mass will tend to pull the spring towards the direction of motion, and therefore it will result in an extension of the spring. Or in other words, I can say that the length would be the natural length plus an additional length, say x. Okay, so this is the primary thing. If you're not able to visualize this, then I think things would become really complex to understand. So I want you to understand this. Say for example, you have tied a spring to let us say to a pen, and you are holding that pen, and to that string, to one end of the string, you are using you are tied a mass to it, and when you rotate it using your hands, what do you feel? You feel that as you start rotating, and after some particular velocity, what will happen? The string will undergo stretching, right? So please try to visualize that. This was the best that I could do. Try using a software here. Please try to do visualize it, and you'll understand it better. Okay, if you have done that part well, let us now go to the next portion here. So this should what you should be, the one I was suggesting sometime before is to visualize it. So when you have the spring in the natural length, string is attached to a point. But when the same string attached to a point undergoes circular motion, the radius of the circular motion is not the natural length, it is instead natural length plus the extended length. Okay, I hope you get that concept, that visualization. If that point is clear, we can draw the free body diagram of this mass which is attached to the spring. Mind you, this mass is undergoing circular motion as well. Why? Because the spring is undergoing circular motion. So by virtue of inertia, the mass will also undergo circular motion, which is being represented here. If I draw the free body diagram of this mass, which is placed on a surface, what can I say the primary force would be? The primary force would be weight of the body acting downwards. The second force would be normal reaction on this mass due to the surface. And what? Exactly, and there would be one more force, which would be the centripetal force, right? Which would be the F centripetal force, which will be acting towards the center, right? So it will be acting towards this, right? Okay, now from this free body diagram, if we apply Newton's second law of motion, see, this body is not bouncing away from the table, it is restricted to the table, right? So we can say that sigma a f y, which is equal to m into ay, is equal to 0. Why? Because there is no vertical motion, right? Now, if there is no vertical motion, the object is restricted along the horizontal surface. Therefore, sigma fx would be equal to m into ax. What is sigma fx? Sigma fx means sum of all the forces acting along the x direction, and there is only one force which is acting along the x direction, which is the centripetal force, and therefore we have F centripetal is equal to mass into acceleration. What kind of acceleration? The motion being circular in nature, the only acceleration would be the centripetal acceleration, which can be written as omega square into r. Now, what is F centripetal? See, like we have discussed in many of the questions, that we have practiced before, we know that centripetal force is not the actual force. There is some other valid existing force that behaves to be a centripetal force, which in this case is the spring force, which acts as the centripetal force. Therefore, F centripetal can be replaced by F spring, which can be written as Kx, right? So we have Kx is equal to m into omega square into r. What is r? Is it the length of the spring? No, it is not the natural length of the spring. It would be natural length of the spring plus the extension. Now, if I take m omega square within the brackets, we have m omega square into L plus m omega square into x. I'll transpose m omega square x to the LHS. So we have kx minus m omega square x is equal to m into omega square into L. And from this, we have x is equal to m omega square L by k minus m omega square. Let us now substitute the values. What do we have here? The value of m is 100 gram, so 0.1 kilogram. Omega square is 5 rad per second, so 5 square. Into length of the spring is 20 centimeter, which is 0.2. K is 7.5, given to us as 7.5 Newton per meter. M is 0.1, omega square is 0.5. So we have 0.1 into 0.2, 0.02. 5 square is 25, right? And then we have 0.1 into 5 square. 25 is 5 square is 25 into 0.1 is 2.5. 7.5 minus 2.5 is 5, and 0.5 by 5. Now, see, even when I was doing this for the first time, I have to admit that I was wrong in this step. We tend to be, at times overconfident with the calculations. I know what I did was I just wrote it like this. I wrote it 50 per 5 is equal to 10. So that things happen. Yeah. Okay. So anyway, so the correct option here would be multiplying this with 10 on both numerator and denominator, which is 5 by 10, which is 1 by 10 equal to 0.1. Are we done with the question? No, because the question is not to find out x. What is the question? The question is to find out the tension. And what is the tension in the spring here? It is the spring force. And what is the spring force? It is equal to kx. What is the value of k? 7.5. What it is x? We just found out to be 0.1. Therefore, that's become 75 into 0.1, which is 0.75 Newton. Okay, so that's how we do the question in inertial frame. Now, how would things be different when we try to approach the same question in a non-inertial frame? Like, what force would come into picture when we discuss non-inertial frame? Exactly, when we discuss non-inertial frame, the concept of pseudo force has to be addressed, right? So let's try solving the same question using non-inertial frame. So now we'll try to solve this question using the non-inertial frame method, right? So when we solve it using non-inertial frame method, all we need to understand is primarily the difference between inertial and the non-inertial frame. Now from this diagram, it should be clear to you that here we have the observer is observing the block with respect to this block. Okay. Earlier he was standing here on the ground and then visualizing the block. Now what is he doing? He is observing this block with respect to the block. Now it doesn't mean literally or physically that the man is standing on the block. No, because if he stands on the block, then there will be an added force of normal reaction. So that is what we are talking about. We are just trying to say that he is observing things with respect to the block. So it is not that the man is standing on the block. He is observing with respect to the block. Okay. Okay. So that's one point. Second, what is a non-inertial frame? Let's see that first. A non-inertial frame is a reference frame that is accelerating or rotating. So we have, what did we say non-inertial frame as? The block. What is the block doing? It is accelerating. What is the block doing? It is in a circular motion. In such frames, Newton's laws of motion do not apply in their simplest form. Why? Because there is a need of additional pseudo force or frictious force or inertial force, which has to be added to. Why has it to be added? Because to account for the acceleration of the frame itself. Okay, this basically translates. So this is, suppose this is point A, and we have the stretched spring here. Attached to this is the block, and if there is an observer standing here and is observing this block from this point of view, then there will be two forces. One will be the force of tension, definitely, and the other would be the pseudo force which acts like this. Okay, things will become more clear when you make a note of this, draw this diagram, this as well, and try to read it on your own. Things will start making more sense to you. Okay, so I assume you are, writing these things along with me. Now the next question comes up: why do we use a rotating frame? See, in a rotating frame, the centrifugal pseudo force provides a simpler way to calculate the tension in the spring. Really important, tension in the spring. Why? Because it allows us to treat the block as if it were in equilibrium. Now let me just bring this previous diagram here. Give me a second. Sorry to. So what this part is trying to explain is, if you were considering a rotating frame like this, right? You can say that this object here is in equilibrium. And when is this in equilibrium? When the tension in the string, which is moving like this, right, exactly balances the outward pseudo force, making it possible to solve for the tension directly. Okay, so basically what have we done? We have reduced this problem in such a way that all we need to do is consider this object in equilibrium by accounting for a new force, which is the pseudo force. Okay, now see, most of the students have a misconception here. Let me just clear this. This pseudo force is not actually a force. Similarly, this centripetal force here is not actually a force. It is some other force by virtue of which the object tends to be in a circular motion, and any force that causes an object to rotate will be causing a centripetal effect, and therefore it will be causing a centripetal force. So therefore it will be called as a centripetal force. So in this case, this force here is the F centripetal, whereas the outward force here is what we call as the centrifugal force. What I'm trying to say is, these nomenclature, they come into action depending upon the frame of reference. So you cannot choose an inertial frame, right? You cannot choose an inertial frame and then say that you're considering centrifugal force. No, because centrifugal force is a pseudo force, and pseudo force comes into picture only when we use a rotating frame, which is actually a non-inertial frame. Okay, so I hope things make sense here. Okay, just write down these things. It will become more clear to you. Okay, now how do we consider the pseudo force in the rotating frame? Because the string rotate, because of this rotating frame, because this rotating frame is not an inertial frame. Why is it not an inertial frame? Because it is constantly changing direction. Why is it constantly changing direction? Because we know that in a circular motion, right? In a circular motion, every velocity is tangential at every point, right? It is tangential. We need to introduce a pseudo force to account for this effect of rotation. In this case, the centrifugal pseudo force appeared to act outward away from the center point. So let's just try to explain you this concept one more time. So we can say here that the centripetal force acts like this towards A, whereas the centrifugal force acts away from the point A. So this line here represents the F centripetal, whereas this represents the F centrifugal. Okay, and the magnitude of this force, which force? The centrifugal force, is given by m into omega square r. Why? Because this is in a circular motion. Okay. So to summarize, imagine sitting or moving along with the block. From this perspective, the block appears stationary relative to you, even though it is moving in a circular path around point A. So I hope you can make use of this diagram, right? Maybe I just try to bring in the diagram one more time so that things become really easy for you to understand. Okay. So let's say let us say this is the table here, right? And this object here is in circular motion, right? This object here is in circular motion. And what do we need to imagine? We need to imagine that we are sitting on the block, or we are trying to move along with the block. And from that perspective, what actually happens is velocity of the block will be equal to velocity of the observer, which means the relative velocity of the block with respect to the observer will be equal to 0. And it is in this case that we call the frame to be a rotating frame. Okay. Okay, which also reminds me that this is not inertial, this is non-inertial frame. Okay, so now from this perspective, the block appears stationary relative to you. Why does it appear stationary relative to you? Why? Because the relative velocity of the block with respect to the observer is equal to 0. This rotating frame rotates with a constant angular velocity omega, matching that of the block's angular velocity. Relative velocity of block will be equal to relative velocity of observer or relative velocity of the frame. This magnitude is given by m into omega. It is not omega into 2r. It is f is equal to m into omega square r, right? So the rotating frame in this question is a frame of reference moving with the block as it rotates around the point. This is a point A. In this frame, the block appears to be at rest with a balance between the tension and the spring. Okay, so if you want to make a note only of the very limited topic, I think you can just draw this, and then you can represent that here the F, the pseudo force, right? F pseudo is balanced by F centri. This would suffix you the note. Okay. Now, since that we have done this, what can we do next? We can now try to solve the question. And how will you solve the question? Considering the non-inertial frame, sigma fx implies m into a is equal to 0. Why? Why? Because the object is in equilibrium with respect to the observer who is standing on the block, which means the only two forces acting here will be F spring and the other force would be the F pseudo. And since these two forces are vertically since this object is in equilibrium, we can say that vertically the normal reaction and the weight would be cancelled, right? So we can say that sigma Fy is equal to 0 and therefore n will be equal to mg. Now, if sigma Fx is equal to 0, forces acting towards the left, F spring, should be equal to force acting towards the right, which is force pseudo. What is F spring? F spring is kx. What is force pseudo? Mass of the block into acceleration of the block. What is acceleration of the block? It is acceleration of the circular motion. What is acceleration of circular motion? Omega square r, where what is r? R is the radius of the circular path. R is not equal to length of the spring. R is not equal to the natural length of the spring. In fact, what is R is equal to? R is here equal to the extended length of the spring. And what is extended length of the spring? It is equal to the natural length plus the extension, which is L plus X. Therefore, this equation becomes Kx is equal to m into omega square times L plus m into omega square X. Then I'll transpose this portion, right, this to the RHS, and what do we get? Kx minus omega square is equal to m into omega square into L. And then X, I'll take out what common from here. I'll take out this X as common. And what do we get? X into k minus m omega square is equal to m into omega square L. Therefore, X is equal to m omega square by k minus m omega square. Now, with reference to the given question here, what's the value of m? The value of m is 100 gram, 0.1. Angular velocity is 5 rad per second, 5 square. Length of the spring is 20 centimeter, 0.2. 7.5 minus 0.1 into 5. So 5 square is 25. 25 into 0.1 is 2.5. So this becomes 7.5 minus 2.5, which is 5. 25 into 0.02, it becomes 0.5. Multiplying by 10 on both numerator and denominator, what we get is 5 by 50, which is equal to 1 by 10, which is equal to 0.1. Therefore, x is equal to 0.1. And always keep this in mind. The question is to find out the tension in the spring. What is the tension in the spring? Tension in the spring is spring force, which is equal to K into X. And what is the value of K? The value of K is 7.5 from this question, 7.5. And what's the value of X? X we just found out to be 0.1, which gives us the answer as 0.75 Newton. The correct option being option B. See, I have taken much of your time. I do realize that. But what's the intent behind it? The intent behind is to is to show you that you can approach a question in both ways, in an inertial perspective as well as in a non-inertial perspective. Especially when it comes to numericals based on circular motion, if you try to do the questions based on a non-inertial perspective, then most of the time students don't consider the pseudo force, which actually makes them which actually makes it easy to solve the question by considering that object to be in equilibrium than to be in a motion, which helps you in calculating the problem easier. Okay. But having said that, I would also like to say that no matter which approach you use, you have to arrive at the final answer. Therefore, you will have to include all the necessary calculations. So you're not skipping any calculation by choosing a a non-inertial frame. The conceptual difference comes into picture when you use inertial and non-inertial. That's it. You can solve the question in either ways and you will arrive at the same answer. Okay. So that's it with this question. I'm really sorry that I took a really, you know, somewhere around 14 to 15 minutes. It's too much for this one question. Sorry for that. Let's move on to the next question, which is okay. Now, this again is based on work energy power. A very simple question based on application of differentiation and integration. So we have the question: a particle of mass 10 gram moves in a line with retardation 2x, where x is the displacement in SI units. Its loss of kinetic energy for the above displacement is. So this is one such question where well, I see most of the students and especially when we do this question in the exam, exam pressure, we often tend to get confused with this negative sign, with the convention of loss and retardation, the sign convention. We're always confused, should we take vector approach or the scalar approach? See, no matter which approach you choose, you will have to arrive at the same answer. Okay, so let me just take some time to explain that here, so that you don't so that you get used to use these confusing notations at time. So it's given to us that retardation is 2x. Now, when we say retardation is 2x, it means that acceleration is equal to, right? It means acceleration is equal to minus 2x. So to have acceleration is equal to minus 2x, I have written it as minus a is equal to 2x in both cases. Okay. Now, I'm not going to use vector approach here, but let us focus only on the scalar approach. Why? Why? Because kinetic energy is scalar. Work done is scalar, not vector. So we're not going to the vector approach. So we have minus a is equal to 2x. Now coming to the next point here, which is loss of kinetic energy. See, what is loss of kinetic energy? Change in kinetic energy is delta K. Let me just try to explain you that first. So what is change in kinetic energy? Or maybe like this. What is change in kinetic energy? Change in kinetic energy is nothing but kinetic energy final minus kinetic energy initial. And this change in kinetic energy can give you two possible values. One, it could be positive. The other, it could be negative. And if that value, right? And if that value is positive, we have that change in kinetic energy is equal to positive, implies it is a gain in kinetic energy. And maybe so if change in kinetic energy is positive, it implies there's a gain in kinetic energy, which means velocity of the body is increasing. And if change in kinetic energy is negative, it means there is a loss in kinetic energy, which means the velocity of the body is decreasing. Okay, I hope this much is clear. We'll have detailed calculations, and then you'll understand it better. But as of now, just make a note of this. Now please do write along with me so that things become really clear to you. Now, by work energy theorem, we have work done by what? Now, I've been trying to say this almost every question, that whenever you say work energy theorem, you need to mention which kind of work is being done, or to be more precise, work is done by which kind of force. Is it a conservative force? It is a non-conservative force? Is it gravity? Is it friction? You need to mention the specified force. And since in this question there is no specific mention of the force, we assume that the only force acting here is the retarding force, and therefore I've written that work done by the retarding force should be equal to the change in kinetic energy, which could be either loss in kinetic energy or gain in kinetic energy. Now, since it is retardation here, definitely this change in kinetic energy has to be loss or negative. So what is work done? It is F dot dx. What is F? Ma. What is A here? Minus 2x. So I've taken minus m outside. Okay, outside the integral. So now I can write here that minus m into integral a dx. What is A? A is minus 2x. So I have taken A. Instead of writing it is minus 2x here, I already taken the minus outside. It is 2x now. So what is integral here? Upper limit is x, lower limit is 0. Integral of 2x is x square. Applying upper limit, x square at x is x square at 0 is 0 square, x square minus 0 square is x square. Now we have delta k is equal to, right? So what is this? All of this is delta ke is equal to, what is this? This is delta ke is equal to minus 0.01 into x square. Now it is given to us in the question that the loss in kinetic energy is, it is not a change in kinetic energy. What is given to us? It is given to us that the loss in kinetic energy is equal to x upon 10 to the whole to the power n, right? So we have not been given change in kinetic energy. What we've been given? Loss in kinetic energy. So loss in kinetic energy, this is where the point comes. Yeah. So if we say loss in kinetic energy is given to us, then what is that we have? We have is negative delta k. If gain was given, it would be positive delta k, and that is why when we say since loss is given, this value will be equal to not negative, it will be equal to positive. Okay, why? Because loss is equal to negative delta k. Let me just write it down one more time here. So what is loss in k is equal to? Loss in k is equal to negative delta k, right? Or maybe we can write it like this. Loss in k is when ke is equal to a negative value. Okay, so I hope that portion is clear. Now we have, if we just arrange 0.01 as 1 by 10 square, right? Because 0.01 is 1 by 100, 1 by 10 square. You can compare this value here. N is 2 and LHS x to the power n, RHS is x to the power 2, so n has to be 2. Other way around, 10 to the power n, 10 to the power 2, again n is 2. Okay, so yeah, so that's what we have here. Now if you have any confusion here, I can just give you an example to in the meanwhile you can just make a note of this complete portion. I'll just explain you this portion also. So we have a final initial velocity as 3, final velocity of as 1 meter per second. So what is change in kinetic energy? Change in kinetic half into m into final velocity square minus initial velocity square. So it is 1 minus 9, which is minus 8. So now we have change in kinetic energy is equal to minus 8. And what does it imply? When change in kinetic energy is minus 8, it implies that loss of kinetic energy is equal to 8. And that's how we come to this plus sign here. So I hope the scalar approach is clear to you, and I hope that there's no confusion regarding this adoption of sign and conventions. Okay. So yes, now let's move on to the next question. So now a body is dropped on ground from a height h1, and after hitting the ground it rebounds to height h2. So we have h1, ball is dropped, then it rebounds to height h2. If the ratio of velocities of the ball of the body just before and after hitting ground, before, so let us say before hitting the ball it is v1, and let us say after hitting the ball it is v2, then the percentage wait ratio of velocities of the body just before and after hitting, which means there is a minor mistake here, which means v1 by v2 should be equal to 4, and therefore v1 should be equal to 4v2, right? So v1 should be equal to 4v2. Let the respective kinetic energies be k1 and k2. Therefore, what is change in kinetic energy? Final kinetic energy, that is after k2, minus initial kinetic energy, that is before k1, the whole upon k1 into 100, right? So, well, see, if you can, if you want, you can try doing it in the coefficient of distribution approach. But it really doesn't make much of a difference here, because the overall point is to calculate the percentage loss in kinetic energy. So, how do we do that? What is kinetic energy 1? K1 is equal to half mv1 squared. What is kinetic energy 2? K2, it is half mv2 squared. Now, what do 1 and 2 represent? This represents before collision and this represents after collision. But what is v2? We wrote that earlier, that v1 upon v2 is equal to 4. Or in other words, what is v2? v2 would be equal to v1 upon 4, right? So what is v2 square? It would be v1 by 4 the whole square. Now I'll make a small rearrangement here. I'll write it as half m into, I'll take this v1 square outside, so I'll take half m v1 square into 1 by 4 square is 1 by 16 into 1 by 16. Now what is half m v1 square? Exactly, half m v1 square is k1. So we can write k2 is equal to, instead of this half mv1 square, what do we have? We have k1. So what is k2 is equal to? So k2 is now equal to k1 into 1 by 16, or k1 upon 16. Now percentage change in kinetic energy, right? Percentage change in kinetic energy is nothing but final minus initial by initial into 100. What is final? K2. What is the value of k2? We just find out the value of k2 to be k1 upon 16. So we have k1 upon 16 minus k1. So what is k1 upon 16 minus k1? It is k1 minus 16, the whole upon 16, which I can write it further as the whole upon k1 as 16 into k1, right? So we have k1 minus 16. What is, sorry, k1 minus 16 k1, which is minus 15 k1. So ideally there should be minus 15 k1, and what's the denominator? We have k1 as well. Now what is k1 by k1? k1 by k1 is 1, and therefore I can take this as minus 15 by 16 into 100. Now what is given in the question? See, this is where the scalar approach and the magnitude negative and positive comes into picture, and the significance of it. Now minus 15 by 16 into 100 can be written as minus 15 by 4 into 25, which is equal to the percentage loss in kinetic energy is given by x by 4. Now what we have found out is not percentage loss, it is the percentage change. Now what is the percentage change? It is minus 15 to 25 by 4. Now if percentage change in kinetic energy is minus 2, what does it imply? It implies that the loss is equal to 2 and not minus 2. Okay, so loss is equal to 2, otherwise it implies that the percentage kinetic change is minus 2. Similarly, when the percentage change in kinetic energy is minus 15 by 4 into 25, it implies that loss is equal to plus 15 by 4 into 25. Now what is 15 25? It is What is 15 25 by 4? It is equal to x by 4. Where does x by 4 come? Because we have given the question as the percentage loss is x by 4. So if two fractions are equal, if the denominators are equal, the numerator should also be equal. So we have 15 into 25, which is 375. So the correct option here would be 375. Okay. So very simple, straightforward question. Now let us move on to the next one, which is based on, wow, now this is a very good question because it connects your concepts with not loss of motion, motion in a plane, projectile motion. So since this question is based on projectile motion, what I would suggest is let's have a quick recap about the basics of projectile motion, right? And then we'll try to answer these questions based on the discussion. So we know when a body is in projectile motion, it can be expressed as a combination of two motions. One along the x-axis with velocity vx and other with along the y-axis with velocity vy. Or in other words, projectile motion can be expressed as vertical motion plus horizontal motion. Now what does this mean? This means that if you project an object with velocity v at an angle theta, right, it will always have two components of velocity. One, which is the horizontal velocity, and the other, which is the vertical velocity. Okay. Now, as the object goes up, one thing remains constant, which is the horizontal component of velocity. So the horizontal component of velocity remains constant throughout. It remains constant throughout. But what varies is the vertical component. The vertical component, since acceleration due to gravity is always pulling it downwards, during the motion from point of launch O till A, acceleration due to gravity would actually pull down this object, and at every consecutive point the vertical velocity would reduce in its magnitude. Therefore, here the vector would be smaller. Here the vector would be even smaller, and here the vector wouldn't exist at all. Now, after A, what happens is the acceleration due to gravity would try to pull this towards it. Therefore, it will result in an increase in velocity, and you could see that the magnitude of the vector is the same, the only difference being the direction. Now we have the same magnitude of vector here, but so if you compare these two vector diagrams, the difference is both of them have a horizontal component of velocity and have an equal vertical velocity, but in the opposite direction. This is towards north, this is towards south. And then as the last one, we also have this component of velocity like here, right? And of course we can also say that the net direction of net velocity would be something like this, and here we only have one component of velocity, which is the horizontal velocity. Here the net velocity would be like this, and here it would be like this. Okay, so this is the basic about projectile motion. Now what's interesting to understand here is this point A is very critical to us, especially in this question. Why? Because A is the maximum height, right? A is the maximum height, and in this height V, which can be written as root of Vx square plus Vy square, or say V at A, which can be written as root of Vx at A square plus Vy at A square, right? Okay, let me keep this discussion posted for a second. Let me just take you through so this is where I want you to make a note of things here. Okay, so what is the behavior of a particle, behavior of an object which is under projectile motion? When a body is projected at an angle from theta, from the ground at an angle theta, it follows a parabolic trajectory. Okay, this motion can be broken into two components. One, which is the horizontal component at constant velocity, since there is no horizontal force, ignoring air resistance. So this component. So the horizontal motion is constant in nature. Second one is vertical motion, which is affected by gravity, which causes the vertical velocity to decrease as the object rises and then increase as the object comes down. Okay, so if you have written down this, observation, and if you were really concentrating during the previous the diagram, I think concepts would be clear by now. If you have not, or if you find, recollecting projectile motion difficult, I just try to give you a brief recap. Okay, now let us go through each and every statement given to us here. So the statement 1 says the vertical component of momentum is maximum at the highest point. Now, again, if you are new to this topic, or if you feel that you need a recap, please make sure that you make a note of these things. So, for statement A, the vertical component of momentum is maximum at the highest point. See, at the highest point, the vertical component of velocity is 0, right? As gravity has decelerated the vertical motion to a stop at this point before pulling it back down, which means from this point, as the object is going up, right? As the object is going up like this, what will reduce? Let us see. What reduces is, this was the earlier vertical component. Now the vector has reduced further. And here there is no vertical component at all. The gravity has decelerated the vertical motion, which means the magnitude of the Vy component is becoming less. To a stop, here it is 0, right? So at this point, I can write that, Vy is equal to 0. Since the momentum is mass into velocity, and the vertical velocity is 0, the vertical component of momentum is also 0. Okay, which means statement A is incorrect. Now let me just, please make sure that you make a note of these things first, right? Make a note of these things, and then we'll try to do it mathematically. So I can say that at the topmost point, the only velocity is Vx is equal to V cos theta, right? And Vy is equal to 0. Now we have Vx is equal to V cos theta and Vy is equal to 0. Now what is Py? Py will be equal to m into Vy. What is Py? Py is the linear momentum along the which direction? Along the y direction. So since Vy is equal to 0, we can have that Py is also equal to 0. Okay, I hope that makes sense. Very simple concept. Now let us go to the second statement. What does it say? It says that for a body projected at an angle with the horizontal from the ground, choose the correct statement. The kinetic energy, I'm sorry, okay, this was the question directly. The kinetic energy is 0 at the highest point of the projectile motion. See, the kinetic energy is 0 at the highest point of projectile motion. At the highest point, the object still has a horizontal component of velocity, which means it still has kinetic energy. Along which direction? Of course, along the horizontal direction. Only the vertical component of velocity is 0. Kinetic energy depends on the total velocity, and since there is still horizontal motion, or in other words, since there is some total velocity, kinetic energy would not be 0, and therefore the statement is incorrect. Let us try to understand that mathematically and graphically. So what we have here is, when we have a projectile motion, right? When we have projectile motion passing like this, as it reaches the highest point here, say this is O and this is A. As it reaches A, we need to understand that at A, Vy is definitely equal to 0. Why? Because as I've represented here, the magnitude of this velocity vector along the y component, it diminishes to 0 at A. But what we also need to understand is at A, velocity along the x component is still equal to V into cos theta, right? Now, at highest component, what is kinetic energy is equal to? Kinetic energy at highest point h max or height max is equal to half m into v at h max square, half mv square. Now what is vh max square? Vh max square is actually the resultant of Vx square plus Vy square. Now, what is Vx square? What is Vx square? Vx is V cos theta, Vy is 0. Therefore, V at h will be equal to root of Vx square plus Vy square, which is equal to root of V square cos square theta plus 0, which is equal to V cos theta. So V at h is equal to V cos theta. And therefore, what is kinetic energy at the maximum height? It is half into mv square cos square theta, and definitely this is not equal to 0. And why is it not equal to 0? Because V is not equal to 0, because m is not equal to 0, and because theta is not equal to 0. Okay, I hope that makes sense. Now, let us come to statement number 3. See, now this is one such point where I think conceptually a lot of students don't try to emphasize much on the concepts here, both in the theory part and in the mathematical sense. Let us see the basic theory here. So the gravitational potential energy is maximum at highest point is what the statement says. Now the gravitational potential energy, which we can generalize as mgh, depends on the height h above the ground. Now see, this is the point where I would say concepts should be really strong. It necessarily need not be on the ground always. What I mean is there can be a zero reference chosen for this gravitational potential energy, which can either be the ground or which can, that is arbitrary. You can choose it anywhere along the plane. Now, at highest point of projectile motion, the object is at its maximum height. So when the object is projected from A at an angle theta with velocity v, it will travel like this, and slowly it will come to this maximum height b, right? And at the highest point at B, the object is at its maximum height, meaning the gravitational potential energy is also at its maximum, this point. Therefore, C is correct. Now, let us just try to go through, let us try to connect the chapter gravitation and work energy power here. See, by the theory that we learned in gravitation, what is gravitational potential energy? U is equal to, it is mgr into h by h plus r. But since these projectile motion take place very close to the surface of Earth, I would like to repeat that point. Since this projectile motion takes place very close to the surface of Earth, we can say that when compared to the radius of the Earth, this height is really very less, extremely less. And since it is extremely less, we can therefore approximate r plus h as r. And then what we get is, instead of r plus h, we can substitute that with r, and r by r becomes 1, and therefore u is equal to mgh. Now what is this h? In this specific example, we have considered h to be the surface of the Earth, but it doesn't mean that it always has to be the surface of the Earth. When you say that potential energy U is equal to mgh, what we need to understand is when we use this formula directly, you can take any zero reference to calculate height. Okay, I'll just do one example for you. So say in this case, okay, so in this case, if you see, I've got this blue line here as the zero reference. Okay, what am I trying to say? Give me a second. So this is the x-axis, right? This is the y-axis, and now we have a reference axis here, a zero reference. So this is a zero reference would be considered as h is equal to 0. This zero reference would be considered as h is equal to 0. Now, this point A, the gravitational potential energy at point A would be equal to m into g into height of this point A with respect to zero reference. What is the height of A with respect to zero reference? Since they are on the same line, the height with respect to zero reference is equal to 0, and therefore this value is 0. Similarly, when it comes to C, what is the gravitational potential energy at C? It is equal to m into g into height of this point C with respect to the zero reference. And where is C located? C is located exactly on this zero reference, and therefore the height is also equal to 0, and therefore the gravitational potential energy can be assumed to be 0 here. Now, at B, what is gravitational potential energy at B? It will be equal to mass into g into height of this point B with respect to the zero reference. And with respect to zero reference, this height is h max, and therefore GPE should be equal to GPE max. Okay. Now, of course, this is a very basic thing. Now, what I want you to do is, I want you to solve the same question by keeping the reference axis as a line passing through B. What will you do? You will redraw this question, you will redraw this diagram, right? And you will take the statement like this. By considering B to be the point through which the zero reference passes. So this is your zero reference now. This is your zero reference. And you will do this calculation with respect to this zero reference, and then tell me how will the value vary for GPEA, GPEB, and GPC, and what will you be your conclusion. Okay. Okay, so having said that, let us now move on to the last section. So here the statement says the horizontal component of velocity is 0. The horizontal component of velocity is 0 at highest point. In a projectile motion, if you ignore the air resistance, the horizontal component of velocity will always remain constant throughout the motion. Something that we're discussing right from the first diagram. So say if this object is projected at the velocity u, right? Velocity u, there will be two components. One is the horizontal component, and the other would be the vertical component, right? And the horizontal component would remain the same. Horizontal component would remain the same throughout the motion. Okay. The horizontal component does not become 0 at the highest point. Instead, what becomes 0 here? What becomes 0 here is the vertical component that becomes 0. The horizontal component does not become 0 at the highest point. It stays the same as it was at the launch. Therefore, D is also incorrect. So we have the correct option to be option C. Okay, so okay, now since let me just take one more second to explain this one. So since there is no force along the x direction, right? Since there is no force in the horizontal direction, mass into acceleration in the horizontal direction would be equal to 0, or in other words, acceleration in the horizontal direction would be equal to 0. And since ax is equal to 0, what is vx is equal to? Vx will be equal to ux, which means the final velocity will be equal to initial velocity throughout this projectile motion. Okay. Okay, so that's it. This question. I would request you to make a note of this. Okay, write this with me for one time. See, this will take a long time to explain. So say I have taken somewhere around 15 minutes to explain this. When you make a note of this, it will take you almost the same time. But once you have done making the note of this, once you have written it on your own, once you have solved this question by understanding the concept, the coming questions would take only 3 or 5 minutes, or maybe even less than that. Okay. So the point is always focus on what the concept, which concept is being demanded in the question. What is the question paper setter trying to judge you in that question? What's the concept that he's trying to evaluate you on? Okay. So since this was basically not something based on this chapter, it was based on a question from work energy power, but it was intended to check your concepts on projectile motion. Okay. All right. Now moving on to the next question. There is a minor correction in the question given here. So it says a lift of mass m is equal to 500 kilogram is descending with speed of 2 meter per second. Its supporting cable begins to slip, thus allowing it to fall with a constant acceleration of 2 meter per second square. Find the kinetic energy when the tube comes to a fall of distance of 6 meter. See, let me take some time to, you know, to emphasize on this phrase here, which is begins to slip. It's really important that we understand each and every phrase given in the question, because there is always a concept hidden, behind these phrases given in the question. So, when we say that the cable supporting the lift begins to slip, okay, it implies a change in the interaction. Let me just highlight this. Begins to slip. It implies a change in the interaction between the lift and the cable due to reduced friction or loss of grip. This change results in relative motion between the lift and the cable. If we consider VL to be velocity of the lift and VC to be velocity of cable, before slipping, velocity of lift is equal to velocity of cable, which means the lift and cable are traveling together, right? Which means I'll just in a minute I'll take you to the diagram. So this is lift, okay. So that is the cable. This is the cable, and then we have here the lift. When the velocity of cable is equal to velocity of lift, the relative velocity between them is velocity of lift with respect to cable is equal to velocity of lift minus velocity of cable. Since both of them are equal, this would be equal to 0. However, after slipping, what happens is relative motion comes into picture, which means the lift and the cable are now traveling at two different speeds, and therefore velocity of lift with respect to cable is not equal to 0. So before slipping, the lift was descending at a constant speed. Now what has happened? Now it is no longer at a constant speed. In fact, it is coming down with a net downward acceleration of 2 meter per second square. Okay, so this is what I want to understand, because it's really important that that we always try to understand each and every phrase that is given, because when you get such a clarity in the question, things will become really easy for you to calculate and understand, most importantly. So now what we'll do is we'll go into the numerical part here. But before that, let us just visualize this portion here. So we have VL is equal to VC, which means before there was no slipping, right? Before there was slipping, the no slip condition, velocity of the lift, right? Velocity of the lift here will be equal to velocity of the cable, because they are traveling together. So velocity of lift VL is equal to VC. And when slip occurs, there is somehow a loss of contact between the cable and the lift, right? So the lift is now free from the cable, and velocity of lift will definitely not be equal to velocity of cable. And it is given to us that this lift is coming down with an acceleration equal to 2 meter per second square. Okay, and it is also given that after slipping, the distance traveled by this lift is 6 meter, and we've been asked to find out the velocity of this. We've been asked to find out the kinetic energy of this lift at the end of this 6 meter. Okay, so at this point, the lift was coming with velocity u is equal to 2 meter per second. Then it has been under the influence of acceleration. We've been asked to find out the kinetic energy at this point, which means we'll have to first find out the velocity at this point, right? And then we have velocity square into m by 2, we'll get the answer. Now, to do that, what we'll do is we'll make use of the kinematic equations of motion, right? So what is the initial velocity given to us as? It is given to us as 2 meter per second. What is the acceleration given to us as? It is given as 2 meter per second square. And it is given that the lift has traveled 6 meters. So by displacement time relationship, we have v squared minus u squared is equal to 2as. U is 2, 2 square. Then we have A is 2, so this becomes 2 into 2, 4, 6, 24. 24 plus 4 is 28. And once we get the value of V square, right? Once we get the value of V square, kinetic energy would be equal to half m into V square. Half m into mass of the lift is given to us as 500 into 28. 28 by 2 is 14. 14 into 5 is 70. 70 followed by 2 zeros. 70 followed by 2 is 7,000 joules. Now, this is one point where, for the while I was doing for the first time, my answer was wrong. I do remember this because see, this is an integer type question and you need to feed in answer, and the answer here is expressed in kilojoules, which means 7,000 joules can be written as 7 into 1,000 joules, and 1,000 joules is kilojoule. Therefore, the answer here would be 7 kilojoules. Okay. All right. So that's it with this question. Let us move on to the next one. A 0.4 kilogram mass. So this is the 0.4 kilogram mass when dropped from a certain height. So this height, this complete height here is P. At t is equal to 0, dropped, which means the initial velocity should be equal to 0, right? Above the surface of the earth, P. So I've considered this blue line here to be the surface of the earth. The loss of potential energy in the last second of fall is, see, how many seconds will it take to reach the bottom, the surface of the earth? It is 8 seconds. So this line here represents distance traveled in 8 seconds or height traveled in 8 seconds. So what does it mean in the last second? Last second means distance traveled in the last second means distance traveled in 8 seconds minus distance traveled in 7 seconds. So basically, we've been asked to find out this much distance traveled in the last second. And how would you do that? Basic geometry. You have this complete distance here, right? So if I were to draw like, so if you subtract this much distance, right? So maybe I can write it as A, B, and then CD. If you subtract CD from AB, what do you get? What you get is distance traveled in the last second. And how can you do that? We have the direct formula for this. Displacement in the nth second is equal to U plus G by 2 into 2n minus 1. And if we were to apply that, what do we get? Displacement in nth second is, so since the total distance, since the motion was totally for 8 seconds, we have n is equal to 8 seconds, the last second is equal to n is equal to 8. Since it has dropped, we have u is equal to 0. G by 2 is 10 by 2, 2 into 8 minus 1, 16 minus 1 is 15, 10 by 2 is 5, 15 into 5 is 75. Now, it means that the distance traveled in the last second is 75 meters. Now, what will be change in potential energy? Change in potential energy in the last second to be important. Change in potential energy in the last second would be equal to delta U, which is equal to m into g into distance in the last second, which is 75. 75 into 4 is 300 into, 75 into 0.4 into 10 is 300 joules. Now, if you want to do it in a very detailed way, then we can make use of the complete calculation, which would go like this, right? Using kinematic equations of motion. What is S is equal to ut plus half at square. Since the motion is taking place in a vertical direction, we can write that Sy is equal to uy into t plus half ay into t square. Now, since this object is falling from rest, what will be the acceleration direction? What will be the direction of acceleration to gravity? How would you take it as? We'll take the magnitude as positive g, right? And therefore, this equation can be reframed as Sy is equal to, dropped from rest, this will become 0. This will be written as plus Ay can be written as plus g by 2 into what? Into t square. And this is Sy. So first we'll find out S at 8. What is S at 8? S at 8 will be equal to g by 2. I'll write it as 5. 10 by 2, 5. into t square, which is 8 square. 8 square is 64, and then we have 64 into 5. 5 4 so 20, 320, right? And what is S7? S7 will be distance fallen in the first 7 seconds, which will be equal to 0 plus 0 plus g by 2, which is 5 into 7 square. 7 square is 30. 7 square is 49. So we have 49 into 5. 9 5s are 45. 5 4s are 20 plus 4, 24. So we have 245. Right? Now, what is distance fallen in the last second? It will be distance traveled in the 8 seconds minus distance traveled in the 7 seconds, which would be equal to 320 minus 245. So we got 320 minus 245, which is 75, right? So this would be equal to 75 meter. And what is the loss of potential energy in the last second? It will be equal to mass into acceleration into gravity into distance fallen in the last second, which is equal to 75. And we get the same answer again, m into g into 75 meter. The correct answer being, okay, what was the mass? The mass is 0.4 into g is 10 into 75 is 300. Okay, very straightforward question. You can do it in, that depends upon you to choose the shortest way or to go for I think being a JEE main exam, you should be able to in the first formula itself, right, directly get the answer. Okay, let's now move on to the next question. This was a relatively very simple question. Moving on to the next one now. So this question, we'll try to solve it first using laws of motion. So we have an object of mass m. This is object of mass m. Smooth horizontal plane, which means friction is which means coefficient of friction is equal to 0, right? Force is 2 Newton. There is a minor mistake, is angle theta, which is equal to kx. Okay, varies as kx, and x is the distance covered by the object from its initial position. So I'll mark this as initial position. Say this is x equal to 0, and this is at x equal to x. Okay, at x equal to x. The initial velocity is 0, so this is u is equal to 0, and the final velocity is v. Okay, so these two terms are really important. 0 to x and 0 to v. Okay, so x is varying from 0 to x, and velocity is varying from 0 to v. Now, while we approach a question in laws of motion, what is the this can't be generalized, but in most of the cases, we can solve any question in laws of motion by using these 4 steps. Visualizing first, visualization, choosing a frame of reference. I will choose the frame of reference that the observer is standing in an inertial frame. Drawing the free body diagram. I got the free body diagram here, and then sigma fx, sigma fy, and then solve. So we will go through the free body diagram and sigma fx fy part. So this is the free body diagram over here, right? This force F is equal to 2 Newton can be resolved into 2 components. One, the horizontal component F cos theta, and the vertical component F sin theta. Now, since there is no motion along the x direction, right? Since there is no motion along the y direction, why? Because you see, this object is restricted only along the x-axis. This is moving only along the x-axis. There is no upward movement of this block. So we can therefore say that displacement along y direction is equal to 0. And if you differentiate this equation, what do you get? What we get is velocity along y direction is equal to 0, and therefore acceleration along y direction is equal to 0. And if acceleration along y direction is equal to 0, if you multiply this by m, what do you get? M into ay is equal to 0. And what is m into ay? M into ay is sigma fy, and therefore what do we have? Sigma fy is equal to 0. So that is first condition. Now if we apply sigma fx, what is sigma fx is equal to, since there is a definite motion along the x direction, we can write that sigma fx is equal to m into ax. What is ax? See, I have made a small algebraic manipulation here with respect to ax. I can write a is equal to dv by dt, right? And dv by dt can further be written as dv by dx into dx by dt. Okay. And what is dx by dt? Dx by dt is velocity again. And what is dv by dx? It remains dv by dx as such. So a can be written as, acceleration can be written as dv by dx times v. Now here I'll introduce v into dv by dx in the place of x. Okay. And what is the value of f? F is 2 Newton. This this dx, what I'll do is I'll transpose this dx to the LHS. So what I get is 2 cos theta into dx is equal to mv dv. And then I will integrate, this is in the variable separable form, right? This is in the variable separable form, and what? And thus can be integrated, right? Since it's in the variable separable form, this can thus be integrated. And while integrating, what do we need? While integrating, what we need is the lower limit of dx and upper limit of dx, dv as well. This is where I said the diagram comes into picture. So as we said that lower limit of x is x equal to 0 and upper limit is x, lower limit of velocity is 0 from rest to velocity till v. Now, which means we can substitute here that lower limit varies from x varying from 0 to x and velocity varying from 0 to v. Now, what is theta? Theta is kx. So cos kx varying from 0 to x and v varying from 0 to v. Now what is the integral of cos x? The integral of cos x is sin x. What is the integral of cos kx? Cos kx integral is sin kx upon k. The whole limit varying from 0 to x. Integral of v is v square by 2 varying from 0 to v. If you apply the limits, what we get is upper limit sin kx, x is replaced by x, minus lower limit x is replaced by 0, so sin 0. What is sin 0? Sin 0 is 0. So this entire term becomes 0. RHS v square by 2 at v is v square by 2 minus at 0 is 0 square by 2. So this term also becomes 0. So basically what we get is 2 into sin kx by k minus sin 0 by 0, which is sin k to 0 by k, which is 0 by k, equal to mv square by 2. This implies 2 by sin, this implies 2 into sin kx by k is equal to mv square by 2. What is mv square by 2? It is the kinetic energy. And what is kinetic energy given to us as? Given to the question, that kinetic energy is n by k sin theta. So kinetic energy is n by k into sin theta. Now if we compare these two equations, we have kx can now be replaced by, it is given in the question that kx is theta, and therefore if you compare these two equations, sin theta, e, k, and the only variable is n and 2. So by comparing these two equations, we can say the value of n is equal to 2. Okay. Now we'll do the same question using work energy theorem. So now let's solve the same question using work energy theorem, right? Work energy theorem. So to do this question using work energy theorem, first we should understand what is work energy theorem. It simply states that work done by a force should be equal to change in kinetic energy of the body, right? So since this F is acting at an angle theta, we should first identify which component of this force is doing the work. Okay, so this force F is equal to 2 Newton can be resolved into two components. One is the horizontal component, right? One is the horizontal component, and two is the vertical component, Now, which among them are doing the work? See, since the object is moving only along the x direction, right? Since the object is moving only along the x direction, which essentially means that since, say, if you consider, most of the students get a doubt here. Let me just clarify this. So if there's an object over here, okay, there's an object over here, and this object is moving only along the x direction. It is not moving along the y direction. It is restricted to move along the x direction. It is restricted to move along the x direction. There will be displacement only along the x direction. Since it is not going up, nor is it going down, I can therefore say that the displacement along the y direction is equal to 0. If we differentiate this equation on both sides with respect to time, we can say that velocity of the object in the y direction is equal to 0. Differentiating again, acceleration in the y direction is equal to 0. Now, if you multiply this with m on both sides, m into ay is equal to 0. What is m into ay? M into ay is fy is equal to 0. And if fy is equal to 0, what will be the work done by this force, fy dy? So fy dy will also be equal to 0, which means work done by the force component in the y direction would be equal to 0. Which means when we consider work energy theorem, we need to consider only the x component. Okay, I hope the logic and the concept is clear here. If that is clear, let us now understand the application of work energy theorem. Okay. So, please excuse me for a second. Let me just make it a bit more legible. I'm sorry for the less font size here. I'm really sorry. Okay, so while we use the work energy theorem, what is work energy theorem? It, according to the work energy theorem, the work done by the force Fx, this time it's been more specific, Fx, on the object over a distance x, right? So this is the distance moved by the object over a distance x, will be equal to increase in this kinetic energy. My bad, it is not increase, it should be change in kinetic energy. Otherwise I can write that work done by the x component of this force Fx is equal to delta Ke, which is equal to Kf minus Ki, right? Now what is Kf? Kinetic energy of this object at this position, right? So here the velocity is v, and in this early position the velocity is u. Why? Because it was at rest. And since the velocity is u, what is the kinetic energy? It would be half m u square, which is equal to half m0 square, which is 0. Therefore, initial kinetic energy is equal to 0, which means change in kinetic energy would be Kef minus Kei, and this Kei is now equal to 0. Therefore, we can say that delta Ke is just equal to the final kinetic energy, which is nothing but the work done. Okay, right? So I hope the way we are arriving at this steps are clear. If that much portion is clear, now we can find out the actual work done. While we find out the work done, what we'll do is we'll find out the work done by the x component over a small displacement, right? Over a small displacement. So which essentially means say this much is dx. Okay, and then we'll integrate this from x equal to 0 to x equal to x. Okay, so we can say that the work done by the variable force Fx is equal to 2 cos kx would be equal to, over a small displacement, dx would be equal to dw is equal to fx dx. What is fx? Fx is 2 cos kx. What is the limit? Would be from 0 to k. So 0 to x. So x varying from 0 to x. Work done would be from 0 to w, right? In which case we can say integral of dw is w, integral of cos kx is sin kx by k. Right? K is a constant. Now applying limits, upper limit sin kx at x is equal to sin kx at 0 is equal to sin k into, instead of x here, what do we have? Instead of x we have 0. Now what is sin 0? Sin 0 is 0, which means this term will get eliminated, right? And then we only have one term. W minus 0 is w, sin kx by k into 2, right? And now we have W is equal to 2 by K into sine Kx by K. What is Kx? Kx is theta. Now what is this work done is equal to? Work done is equal to change in kinetic energy. Change in kinetic energy is kinetic energy final here. Why? Because kinetic energy initial was 0. And according to the question, it is given that the kinetic energy of the object would be E by nk sine theta. So, sorry, E is equal to n by k sine theta. So I can write here kinetic energy final, or in other words, I can write that this is equal to E is equal to n by k sine theta. Now when you compare these two equations, we got sine theta, k, k, which means the only unknown variable is n, which is equal to 2. Therefore, the value of n would be equal to the value of, not x, the value of n would be equal to